So I'm going to give you an example for how we could apply derivatives to our wagon robot project. And I have the wagon here. I just want to show you how it turns before we go to the next problem. So this is the wagon robot. Like where my hand is right now is where the handle is generally attached. It's actually part of the handle. And the way it turns, it's not like a Vex robot where the wheels are always in the same place. It's on this turntable that turns the two front wheels together. So, instead of having one side go faster than another, it turns kind of like a car, like this. And it has a limited turn, like how far the wheels can go in the circle. Say we have our wagon, which is represented by my eraser here, with the front being the part with the white, the back being the part without the white. And we want it to drive along this path. And this path is a map. The x-axis is the x direction in meters, and the y-axis the y-axis in meters. And let's say it goes at a constant speed. So note that this isn't a distance versus time graph. It's an actual physical map, like you would see, map of a school with x and y. So x and y would be north and east or whatever. So we want the wagon to go like that. From x equals -1 to x equals 3 on the function f of x equals x cubed minus 3x squared plus 3. Okay, so what I'm going to do in this example is find the angle that we want the robot to be at any instant in time on this curve. So like I showed you on the wagon, you can, by moving, like connecting a motor to that turntable that turns the wheels, you can have it turn at a specific angle. You don't just tell the speeds the motors to go, you tell it what angle to turn at. So if we can find the angle it needs to be at any x value, that'd be useful. So the first thing, this may not seem like logical, or you may not realize how to do this at first, but by the end of this you should understand it, and I'll have some practice problems that I hope you guys do. So the first thing I would do is I would find the derivative of f of x. And that's, you guys know how to do that by now, that's just the power rule. And by finding the derivative, we're finding, the slope. And I'll explain what that means in this context. So if I had f of x equals x cubed minus 3x squared plus 3, then f prime of x, or dy or dx, or y prime, equals 3 times 1 x to the 3 minus 1 minus 3 times 2 x to the 2 minus 1 plus 0. So f prime of x equals 3x squared minus 6x. So this represents the slope at any point on this graph. Now that doesn't mean speed, it doesn't mean velocity or anything like that, because our x-axis is not time. They are both meters. So we're just essentially saying like how we want it to be positioned at any different time. And if you think about what slope means on this graph, so say, I'm just going to map this curve right there. If I had the slope at this point, just draw a tangent line. The slope is the way the robot's pointing right there. So if I had that here, the robot would be pointing in the direction of the slope, like that. Yep. So since we have that direction, we can use the slope. The definition of slope is delta y over delta x. So if I took this, or sorry, I'll go this way. Delta x, delta y. If I have that slope, I can get, well, I just made a triangle here if you think about it, delta y and delta x. Also, we usually dot components like I was doing there. Get used to that. Don't draw solid lines because it gets confusing. Delta y and delta x, we have the slope. If I call this right here theta, theta is like the Greek letter for angle, I can find theta if I know the slope, because the slope is essentially a fraction. So if the slope at this point was 1/2, say the slope at this value, whatever it is 1/2, then I can use trigonometry to find what the angle is at that point, or should be at that point. If you know trigonometry, you know SOHCAHTOA. And in this application, we only know the opposite side and the adjacent side, so we use tangent. So we know that tangent theta equals the opposite side, which is delta y, opposite side there, over delta x, which is the adjacent side for theta. And we know that delta y over delta x equals slope, or in our case now, the derivative function of f of x, so f prime of x. And if I just want to solve for theta, say theta, and then I'm going to say theta x, since it varies at different x values. Theta at certain x values is, okay, I have f prime of x. To get theta by itself, I'd have to do tangent inverse f prime of x. So theta x, then, we have f prime of x equals tangent inverse 3x squared minus 6x. So, given any x value on this graph, I can find the angle that the robot should be at that value. So say the value of, the graph got kind of erased, but the value of 1, which is about right there, looks like it's downward sloping a bit. Let's find the angle at the value of 1. So theta 1 equals tangent inverse 3 times 1 squared minus 6 times 1, which equals, using my calculator, tangent inverse of 3, and don't worry if you can't see the screen, I'm just typing stuff in. 3 minus 6, says that would be negative 71.6 degrees. And that actually looks pretty accurate. If I, put a straight edge there, that looks at about negative 75 degrees to me. Okay, we can do another one. Let's take it at 2. It looks pretty near to 0. Yeah, theta 2 equals tangent inverse 3 times 2 squared minus 6 times 2. I'm just using this equation that I made. Equals, and then using my calculator again, tangent inverse of 3 times 2 squared minus 6 times 2 equals 0. Oh, it's actually a minimum. Cool. So that's saying it's 0 degrees right there. That means it is horizontal at x equals 2, which I believe, because it's a minimum. And we'll get to that soon, that any maximum or minimum has a slope of 0, and that's a useful thing to know. Okay, so I hope you understood that process that I just used. If not, watch the video again or talk to me, because I think we're going to be doing a lot of things like this in this project. And you'll probably be doing a lot like that in robotics calculus in general. So what I did is I found the derivative. I thought about what slope meant in this application. Slope will mean something different depending on what the axes are on our graph, or the x is in our function and the y is in our function. In this case, the slope was basically the angle, just in fraction form. And moving on from here, be sure to remember the power rule. That's really important. And just open up your mind for different ways you could use the derivative when your axes are different things.